If you are doing the suggested reading, you may have noticed the lectures differ a bit from the textbook. For example, in the lectures, we are focusing on motion along a straight line in one dimension, while the textbook jumps right into motion in 3 dimensions. Also, topics are ordered a bit differently in our lectures than in the textbook. We hope that the differences aren't too large to cause difficulties. However, there's one difference we want to make sure to discuss to avoid confusion. The textbook discusses early on the momentum principle, which we haven't mentioned yet. The punchline is that for the purposes of this course, the momentum principle is the same thing as what we call Newton's second law. Let's discuss how this is so to help us translate the momentum principle as we read through the book. We'll start with Newton's second law in the form we just discussed for predicting the motion future. V final equals V initial plus F net over m delta t. Now let's multiply both sides of the equation by the object's mass, m. From this, we can obtain a new form of Newton's second law. Now we see here 2 terms which have the form of a product, a scalar, the mass, times a vector, the object's velocity. This yields a new vector, which for most problems we'll study in this course, can be thought of as a new quantity, which we'll call the momentum. The vector symbol for momentum is typically written with the letter P. Now, if we use this notation, then we can rewrite Newton's second law in this form, which is what the text calls the momentum principle. Now, we can also write this with a little algebra as delta P equals P final minus P initial equals F net delta t. So now, anytime we see the momentum principle written in the text, we can always translate that into Newton's second law. That's all we'll say about momentum and the momentum principle for now. Later in the course, we'll discuss momentum in more detail, and we will revisit and revise as needed what we have said here.